So welcome everyone. This is another of the EFG webinars in a number of series that we are offering this year, entitled Digital Outcrops and Data Integration in the Metaverse. Powerful combination to reduce subsurface uncertainty. My name is Glen Burridge. I'm the Executive Director of the European Federation of Geologists. I'll be the host of this webinar. The European Federation of Geologists who are organizing these webinars, we do this to foster professional development of our fellow geologists, to increase public awareness of the importance of geoscience. And today I'm happy to present the speakers of this webinar, Claudia Ruiz-Graham and Jurriaan Reijs. Claudia is a geologist and technology entrepreneur with 25 years of industry experience. She has deep expertise in exploration, having worked in oil and gas projects in Azerbaijan, Angola, Norway, the Middle East, Latin America, and the US. She was a member of the BP Exploration Extended Leadership Team and BP Colombia Executive Team, and recently an external exploration advisor to the Ecopetrol. He is the CEO and founder of Immersive Reality, a company which develops immersive technologies with application for energy, mining, engineering, and academia. Their solutions help reduce geological uncertainty in investment decisions, bringing together teams and data in the metaverse. Imaged Reality helps organizations to collaborate and communicate complex environments, improve interpretations, and create a better interaction with multidisciplinary teams, resulting in better decision-making and risk reduction. Dr. Jurriaan Reijs is the Managing Director and Principal Consultant at Energility Geoconsulting. His company offers advice, training, and project development services in carbon storage and geothermal energy. After obtaining a PhD in structural geology from the University of London, he worked 25 years in subsurface exploration, development, and research, and in a wide variety of settings, such as hydrocarbons, carbon capture and storage, CCS, and geothermal. Before his career as a consultant, he worked at Shell in positions such as principal regional geologist, team leader, and venture manager. Jurriaan drilled world-class exploration wells in frontier basins, complex high-pressure and temperature wells, and near-field exploration wells. He led regional studies, seismic acquisition campaigns, and commercial equity acquisitions, dilutions. Jurriaan has worked in over 50 basins globally, based out of the Netherlands, and has worked in Egypt, Australia, and the US. For giving the floor to our speakers today, just to remind you that after the presentation, there will be a question and answer session. I invite you all to propose questions to the presenters through the YouTube chat. This is our new system we're using from now on. And we will select and answer some of those questions at the end of the webinar. So, Claudia and Jurriaan, over to you.
Thank you very much. Glen, first of all, thank you very much for the invitation to participate. It's an honor to be presenting today at the European Federation of Geologists. And hello to everybody who is online. I'm Claudia Ruiz-Graham. I'm a geologist by background, explorer. And 5 years ago, I started my company, Immersive Reality. At the time, I was working for BP and was during one of those downturns of the oil industry. And as happens many times, a lot of people left the organization without having enough time to transfer the skills to the younger generations. And we also stopped unfortunately, sending people to the field. And that happened, I saw that happening on every cycle. So I came across virtual reality and drone technology, and then I thought, well, maybe we can put the two together and enable people to get access to more digital outcrops and digital field trips. And that was how Immersive Reality started. And since then, we've been working for about 5 years, and now we developed this platform, Stratbox. So today, I'm joined by my esteemed colleague, Jurriaan Reijs, who in the second part of this talk, will be talking about the application of digital outcrops to carbon storage and sequestration. Thank you, Jurriaan, for joining me in this adventure today. So the first part of the talk is going to be about the technology and the metaverse and how this helps to reduce subsurface uncertainty. I hope you are seeing my screen. So let me see if I can minimize this. I'll just move it to the next screen. Yes. So what's the key problem we are dealing with is subsurface uncertainty. This is a huge issue for major capital projects in oil and gas and in the energy transition too, in carbon sequestration projects, in geothermal projects, anything that has to do with the subsurface. And we know how important this has become and how now it's part of very important legislations. Here in the UK, the government just announced a huge investment on carbon sequestration projects to help deliver net zero, as an example. So what's the issue with subsurface uncertainty? Subsurface uncertainty can create up to 20% of cost overrun in these major capital projects. So in an industry that invests a year $90 billion, this can represent, $450 billion a year, $1 million a year. So it's quite a lot. So this is how we normally see subsurface when we have seismic. In geothermal projects, we don't even get seismic. So how we should see the subsurface is something like this, very similar to what we see in the ideal world. We will get a picture very similar to what we see in the surface outcrops. But in reality, what we have is this. We have the information given by the seismic that gives us a blurry picture of the subsurface. And the only hard data that we get is that provided by the wells. And this is what contributes to create subsurface uncertainty. So, with the drone technology, now a lot of people are mapping outcrops and creating digital models of outcrops. And what this does is provide additional insights and help the geologists understand analogs for the reservoirs, analogs for the subsurface. So in this example, we see this is on the coast in southern England. We're seeing some Jurassic rocks here, and you see a very nice fault zone. When we take the view from the drone, you see the same fault zone here, but you see that actually the fault carries on here. But what the drone it helps you visualize is that actually this is part of a very large anticlinal structure. So this bird's eye view gives you additional insights that you don't get to see from the outcrop. That's one thing. One very nice application of drone technology is being implemented right now by Cornish Lithium. Cornish Lithium is a company that is mining for lithium in the southwest of the UK, looking in igneous rocks. And if I show you this, this is a 360 image captured with a drone. And you get to see a very nice overview. This is directly from the web page. But what enables them is to integrate information on fractures or information on more detailed images, and all the way from very large scale to small scale. Now, if I go back to the presentation, the other great thing about drone data and digital outcrops is that enable us to gain a further understanding of the architecture of the reservoirs. This is a quote from Professor Ben Miller. He's an emeritus professor from the University of Aberdeen. And he said, virtual outcrops afford views that will not be possible from the ground, which gives a far clearer impression of the overall 3D architecture. What we are seeing here is a beautiful example of a turbidite channel system from Mexico. This is one of the areas that Professor Ben Miller has studied. So when you put together virtual reality and drone technology, you get to see these outcrop models in the metaverse. And through my career, what I learned was that the best way to reduce subsurface uncertainty is when you are able to integrate data, very good quality data, all the way from regional scale, basin scale, down to the microscopic scale. And also when you are able to bring teams together, working together. And that is great teams working together. So that's what we aim to do when we developed Stratbox. Let me show you this. Sorry, actually, let me go back to this. When in virtual reality, when you put your headsets, you are totally surrounded by the terrains, by the models. You can experience the outcrops at real scale. And more important, you can interpret directly in the outcrop. So when you're joining colleagues, everybody knows what you're talking about. You are not just arm waving. You can integrate data. In this case, you have the seismic line all the way from regional scale down to the pore scale, to the microscopic scale. And we're going to show you some of those examples. And you get to collaborate with others from around the world. So this is an example from a colleague from Shell in Houston. He was in Houston, I was in London. What you are seeing is my viewpoint in VR, and he's taking me to see some outcrops from the Eagle Ford shales in Texas. So we started with the big regional view mapping the outcrops on satellite imagery. We are interacting simultaneously here. If I move this forward, we're going to jump into the outcrop.
We made it to the outcrop.
So this is about 10 meters or so?
Yeah, so it's a small outcrop in 10 meters. So, but first, for people put in context and scale, you can see kind of what the actual outcome looks like. So this is a little of, let me show you here.
Just this for a moment. So what you can do is integrate stratigraphic columns, integrate well log columns, and when you get geologists and engineers in the same environment working together, it's a fantastic tool to communicate complex concepts and scales. As you can see here, at the same time, you get to see the outcrop, you get to see the core and thin sections. And in a moment, we're going to show you a live example of that. So then this is another example. This is from a senior explorer, Mark Shan, who had drilled some wells in, this well is from Honduras, and he's comparing the well, he drilled some carbonates, and he's comparing that with the actual outcrop model. This outcrop model are representative phases of a similar reservoir that outcrop in Mallorca in Spain. These are carbonates platforms. And the interesting thing is that he was able to map fracture systems in the outcrop model that he suspected he had in the
lines. You can draw those here, like these ones over here.
Beautiful. And it's interesting that whereas you see a really nice detailed correlation between well log and outcrop, what you see at the seismic scale is less impressive, and that's because the frequency of the data we have is 12 hertz. So we're not going to be able to see this level of detail at seismic. I think this is a great way.
Exactly. So hence, Hence, because on seismic we see this blurry image, that's why it's important to bring those outcrop data to help understand the reservoir in the subsurface. We also have a desktop solution that you'll see in a moment. It enables you access to digital outcrop collection from analogs from around the world. So let's say you are working with deep water outcrops, you can visit analogs of that in Ireland, continental classics in Spain, etc., etc. So we'll see a bit more of that in a second. The other key piece of information are cores and well cores. And many of you will have visited core stores. This will look very familiar to you. You get together with the teams of geoscientists, looking at the core descriptions. You need to get your core laid out, etc., etc. But always only a handful team of geoscientists get to go to the core store, right? Many of those cores and core images are being digitized by a lot of companies or by data centers, core data centers. So what we have done is we created a platform. This is a second platform, the Core Explorer, that enables organizations connect around virtual, we call it the digital twin of the core stores. And let me show you that.
Stratbox Core Explorer is a web-based platform which facilitates organizations on-demand access to their internal collections of well core and related data in an integrated manner. This is done with the automated upload of images and data at the right depths, which allows users to collaborate in the description and interpretation of cores. Correlate geological features from wells of the same or...
So if I fast forward, you can just compare wells from different locations. Imagine you have a well in one basin and well in a different basin or a different reservoir, and you put it side by side, and at the same time collaborate live with other colleagues and integrating automatically, your data from microscopic scale to very large scale. So we're gonna see now. We're gonna now go to a practical example. I'm gonna hand over to Jurriaan, who is gonna take us to is gonna talk to us to the use of digital outcrop models for carbon sequestration projects. As a summary, on Stratbox we have the Stratbox Desktop, Stratbox VR. Which examples you have seen here today, and the Core Explorer. Over to you, Jurriaan.
Thanks, Claudia. Can you give me the next slide, please?
I'm sharing, right? Sorry, I forgot. So let me share.
Yeah, so I'm going to talk to you about the course I developed together with Dr. Tip Mackel. It's the Geoscience of carbon capture and storage, and we use virtual 3D outcrop analogs and virtual core. We felt like for carbon capture and storage, we need to go back to the observations you make from rock, and then think about how that's important for creating value in your carbon storage project. The next training of this is in November. I will share that later, but together with Tip, I developed that. Tip is carbon capture storage expert for the Texas Bureau of Economic Geology. He has worked for more than 16 years in this field. You already know me. I'm Jurriaan Reijs. Can you go to the next slide, please? So when we think about carbon capture and storage, there's a lot of similarities between exploration and production of hydrocarbons, but there's also some differences. And it's good to think about that a little bit. So in terms of seal, we think about the past, where hydrocarbons trapped. With CO2, it's more about will they stay trapped and be injected in there. It's producing versus injecting. They're slightly different fluids. So how they behave, we'll get to that. So it's important to realize a lot of the observations are similar, but they have slightly different implications. How big is your trap? How much hydrocarbon, how much carbon dioxide can you store? And when you think about charge, it's not so much about how something got there, but what would happen when you put in there. You have infinite geological time afterwards, and where will the CO2 go within the system. And then there's some detailed difference with well completion. I won't get into that right here. Let's go to the next slide. So if you think about how carbon dioxide migrates to a reservoir, there's a good example here from the Sleipner CCS site. For more than 25 years, they've been injecting CO2 into a very good, very permeable shore-face sand. But even in there are some baffles. And you see the CO2 goes up, it hits a baffle, it spreads around, and then it finds a point of weakness somewhere and goes up again. And they have been able to monitor it quite nicely with 4D seismic. They have 7 time instances. You can find it on the web. There's a beautiful imagery there where you can see how it migrates to the field. And actually a nice analog that Tip discovered is poison ivy on the side of a parking garage. It does the same thing. It goes upwards to the light, and then when it hits a barrier, it spreads out, and then when it finds a zone to break through, it breaks through and it spreads out again. And it's actually a nice analog for CO2. At least it gives a nice image. Okay, let's go to the next slide. We'll now move in a minute to Stratbox, and I'd like to show you 2 examples. A virtual outcrop example of the Sherwood sandstone at Butley Salterton, that's offshore the Devon coast in the United Kingdom. These are braided fluvial and Aeolian deposit out from the Triassic. And then afterwards we go to the virtual core store and we look at the core from P187. It's a well close to the Dutch coast near Rotterdam, and it's of the lower Triassic Poon sandstein. It's stratigraphically quite equivalent. It's also sandstone reservoir. It's arid, Aeolian, fluvial environment. And we'll look at that a little bit more detail. And what's interesting, P18 is earmarked to become it's at the moment a gas field, but it's nearly depleted. It was earmarked to become a CCS storage site. It's called the PORTHOS project. So I will talk a little bit about that afterwards. So let me switch to Stratbox. Bear with me for a minute. Share. Share screen, there we are. And I need this screen. All right, so this is the Sherwood sandstone of Devon, which I can move it around and we can zoom in a little bit. Let me connect Claudia in here. So Claudia, I think we got briefly disconnected, so you need a new ID. And I'll tell you the ID. It's 572419. And while you get connected, I'll already show you a little bit. So you see already different packages here. These images quite nice. You can zoom in quite close. You see some discontinuities here. So Claudia will talk us through that for a bit.
Okay, I'm connected.
You're connected, good.
Yes.
So you made some observations while I was talking?
Yeah, I'm right now I'm sort of drawing a channel system that I'm seeing here with lateral accretion, and I can see a transition from a lower layer of conglomerates up into a zone of sandstones through a fault. But now you can maybe bring the interpretation to your side. Okay, so let's see what Claudia did. We request the interpretation. We used it in our course. So this is what she just has drawn. So you see here, there's a channel with some internal fabric. She has drawn some package boundaries. And then I guess you have spotted the fault here and then an offset here. So this pebbly bed is down thrown. And also within here, you see that there's some differences in rock. So here it's quite coarse, and here it gets quite fine, perhaps with different permeability, so that may be important. So shall I get your full interpretation in? Or yeah.
That. So in the interest of time, we made something more elaborate beforehand. There it is. So Claudia, what are your main observations?
So basically, we had the 3 units here. A lower unit that's about half of the outcrop, maybe 10 meters thick, up to the yellow horizon. This is predominantly dominated by conglomerates, kind of alluvial deposits. Then you get a second sequence between the yellow and the blue. If you get closer, you will be able to see some subparallel bedding, and then some sort of what they call honeycomb erosion. Yes. And if you move to the right-hand side of the outcrop, you will be able to see that the unit continues all the way to the right-hand side of the outcrop. And actually, right in the middle of it, you get to see some beautiful subparallel bedding. That's slightly affected by a fault to the right. And then above the blue, there are 2 smaller units. One that is characterized by cross-bedding, some beautiful cross-bedding channels that I try to depict that on green. But if you look even farther up, then you get a little bit more of increase on sort of muddy overbanks. I think there is a 4th sequence in there. But the whole unit measures about 20 meters. So overall, I would say, for an oil and gas reservoir, kind of the units between the sandstones with honeycomb lamination, the cross-bedding will be the best part of the reservoir. But what will happen for CCS? What's your thoughts on CCS here?
Yeah, for CCS, obviously the baffles are important. So there's a fault here. If you look close by, then you see some fabric here with maybe shale smearing. So if it's completely sealing or not, we don't know, but it could be that you're injecting this side and it doesn't get in the rest of the compartment. There are examples where CO2 wells in Snøhvit hit a channel, and they were surprised that the pressure was increasing so much. And it turned out that channel had really good reservoir, but it was in the surrounding of much worse reservoir, so it didn't spread to the entire package, but only in that channel. So that's something to think about. If you have a channel here, does it go out of plane, or is everything very well connected? It is all very porous. And another element you might think about, if you inject down here and this coarse-grained material is more permeable, and you have here finer grained material, the CO2 may go up, and then same with the poison ivy, it may go around here and then here finds its way further up. So it's good to think how it migrates to the reservoir and what kind of baffles it finds. So those are
could you draw that? I just couldn't see.
Sure. So let's do that. So the CO2 that comes up here, and then it may go in that direction, and then it will go up here again, and it may hit something else where there's a baffle here, and then it goes up. So you end up with these packages of CO2 that are stuck behind the baffle. So even though on seismic it may look like a big continuous piece of rock, in reality even pretty good sandstone. So the Utsira sandstone at Sleipner, that's over at Darcy, but also there these thin veneers of baffles spread it around, and it doesn't behave evenly. And there you can see that very, very well. All right, I propose, Claudia, we'll move over to the core.
Yep, sounds good.
And I'll do that. I'll load the scene here straight away, so I don't lose the connection. There we go. So let me introduce you to the core. So if we go to this this viewer here, you see a composite log of the P187 well, and you see at the top we have the seal, the Solling formation. There's a gas field that's sealed behind there, and you see the density neutron crossover. And here's the main reservoir. It's the Hardex and sandstone member. And when you go deeper, you get into the Deptford plainstone member. Still has quite a bit of sandstone in there, but it goes quickly to poor reservoir. And you see that they cut quite a bit of core here. So let's have a look at that core. So let's zoom in all the way. oh, wrong mouse button, sorry. So you see this variability here. There's some streaks with high permeability. Here it looks a bit like less permeability. If we can, with the core plugs, we have hyperlinked them, so we can see what permeability actually is. So you see here on this bit, it's 1.8 millidarcy. That's not great. So when you go deeper down, you start to see here some interesting patterns. So on the side here, you get these darker patches that seems to come from the outside, and that's actually where the resin, where the core was impregnated in, starts to imbibe into the core, and it's a sign of permeability. This tends to be when you start to see that you get a better permeability. So you see that here again, I see it here again. I also marked here in green some areas with really low permeability, some baffles. See these black, thin, laminated silts and mudstones. So if you look here, 6 millidarcy, so that's not much. But if we could go here into these areas with a lot of impregnation, you get into nearly 4 darcies. Now that's pretty nice. If you zoom out a little bit, you see more of these baffles here. Another little bit of this black shale layers here for quite low permeability, about 2 millidarcies. And when you go down here, you see again lots of impregnation. Here you see an area that's completely saturated with the resin, it looks like. So if you look at this here, we get oh no, that's not the right one. So here it's still 400 millidarcy. So it's actually the core plug is taken just before the part I was talking about. I'm actually talking about this bit here. So here you see a core plug that goes directly into one of these impregnated zones. Click on that, and then it's more than 10 darcies. So that's a huge variation. So there's areas with baffles, and it varies between tens of millidarcies to 10 darcy. And when you go deeper down, you start to see the permeability decreases. You see much finer laminae, and this impregnation you stop seeing. So the reservoir is decreasing in quality. You see some more baffles. So let's have a look what that looks like in bulk. So here we plotted all these permeabilities against depth over the image viewer, and you see that here at the top it's quite variable, but you have a lot of streaks that are between 1 and 10 darcies and even hundreds of millidarcies. But once you get to, let's say, 35, 80, your permeability is, the majority is below 1 millidarcy, so not so good anymore. What's interesting in CO2 is that good permeability is not always a good thing. When you inject in one of these 10 millidarcy layers, it's almost like injecting into a lake. There's almost no resistance. Or like spraying an aerosol can into the atmosphere. There's pressurized CO2 that may have a supercritical phase or a liquid phase will expand very rapidly, and during this expansion, adiabatic expansion, you get a cooling effect. This is called the Joule-Thomson effect, and this cooling can be considerate and really create a problem. Your annular fluids may freeze. You may get dropout of salts out of your formation water, but also the local cooling and the stress that causes in a rock may cause induced earthquake when that stress front hits a already stressed fault. So those are things they're dealing with in the Netherlands with the PORTHOS project. Claudia, can you take over the slides again?
Yep. Let me share. Yep. To this one?
Yes. Moment. That's the one I meant. So this is a bit about the PORTHOS project. This is where we had that well P18 from. You see here the harbor of Rotterdam. And the plan of the PORTHOS project is that they collect CO2 from a number of industries in the harbor. So Air Liquide, Air Products, ExxonMobil, Shell. They have huge refineries there, and they have like a collection pipeline of CO2, and then it goes into compression offshore, and it gets injected into this depleted gas field. It's a sizable project. It's they reckon it can store about 37 megatons of CO2 and about 2.5 megaton per year for 15 years. Capex of about $500 million, and it's already a little bit delayed, but the final investment decision should be later this year, and then it's operational from 2026. But you will see that it recreates a fully integrated approach. So it's important that the subsurface and the surface work in tandem. Let's go to the next slide. So already alluded on the Joule-Thomson effect. So because this is a depleted gas field and it's copper intermetallised with faults on all sides, and you already saw that permeability at the bottom goes to very low, so there is no aquifer support. So if you extract the gas, you get a really low pressure. So the pressure here is around 40 bars. So if you then inject high pressure in there, you get this adiabatic expansion, the Joule-Thomson effect. And here you see a model of that P-ethane field where they look at how the cooling effect spreads around the injector. And ideally, you would like to maybe place your well in not the highest permeability, so you have a bit more resistance and you can keep the pressure up and ease into the Joule-Thomson effect. But often with depleted gas fields, you will have to deal with the wells that are already there and you reuse them. And in that case, you will have to manage your injection, and that means you may have to start very slow with lower pressures. That's what they do in the PORTHOS. So they start in the gas phase, slowly pressure up the reservoir, and as the reservoir pressure increases, the Joule-Thomson effect decreases, and then they, in the later phase, they can go to liquid or supercritical injection, which is more efficient. So you can see here that looking at the big scale, the outcrop, what the architecture of the rock is, then observe at a smaller scale in the core what variability you already have and what baffles you can see. You can then extrapolate that to an actual project. So this is in a nutshell. In the course, we'll give many more examples. Can we please go to the next slide? So the last course we ran, we gave multiple examples of CCS projects around the world. Those are the yellow dots. These are actual projects where CCS was injected with lessons learned. We show several field trips and core store trips, also from several places around the world, from Malaysia, from Utah and the Netherlands and UK. And the nice thing with a virtual course like this, that participants can join from all over the world and lecturers can be from all over the world. So Tip Meckel, my co-host, sits in Austin, Texas. I sit in The Hague, the Netherlands. And then we had participants from Beijing to Bogota. So it's a nice way to collaborate, and you're demonstrated with Stratbox that participants can log in, they can make the interpretation, we can show that to the group can discuss it. It's a very nice interactive way to learn together in the virtual world. Let's go to the next slide. Let's end with that. So if you're interested in that, please sign up. The next course is in November, and the link to the course will be shared. If you forget the link, if you remember N586 and you type that into the RPS training site, you will find that course. And with that, I'll hand back to Claudia.
Thank you, Jurriaan. Thank you very much. I like to conclude, with this summary slide about the benefits that we see on using these immersive technologies. Definitely a big contribution on subsurface uncertainty, because you are able to integrate different data sets. And also, enables, as you are trying to get projects approved, sometimes it's hard to communicate those technical concepts in an easy way to those non-technical people. So virtual reality or, interaction with, with 3D elements, as the example that we saw before, help with that in a great way. Improve the workflow enhancements. And a great thing is about putting silo data to work. Sometimes we do all these wells analysis, and those wells analysis happen to be in reports in different parts, and integration happens in a PowerPoint and at many times. So bringing together in the virtual world, in an immersive way, enables you to make better use of your data, and again, connecting people across different sites, connecting expertise, and with with energy transition and Subsurface playing a big role on this, a great application of these technologies in CCS and geothermal. Now we can open for questions.
Great, thanks to you both. The future has arrived, hasn't it? We talked about this sort of thing for years, and now it's in front of us, and it's being used in practice. Please, all of you listening in, digest all this and come up with some questions, and please put them on the YouTube chat. While we're just waiting for that, I'll throw in some questions to get us going. Perhaps an obvious one is what you both feel is the relationship with real life field work. We know the practical difficulties of taking digital tools with screens on into the field. There's numerous. So how do you sort of see the balance here between what is done and time spent in a virtual space with compared to having your nose pressed up against the rock?
I'm a geologist who loves being on the field, and I love touching rocks. I love seeing the perspective, as most of geologists, we love being on the field. But what I have discovered with these tools is that if I'm going into a field trip, I can get together with my team and plan what I'm going to see before I go, right? And sometimes for those locations that I'm not able to go, I can bring them into context for the few locations that I'm able to visit. And I think for that is fantastic. The other thing is that because I'm able to do things in virtual reality that I'm not able to do in real life, it makes me get faster insights in other things. To give you an example, we all have been where we are at the edge of a cliff, and we have the field trip instructor pointing to sections in the mountain in the distance, right? You can see that fault that is next to the house with the red top, and everybody, the geologist engineers, where is he pointing? Where is she pointing, right? So many things are lost in the concept like that. And at the same time, you get people, a group of 20 people surrounding a poster size cross section. Yes. In virtual reality, you can put it next to your outcrop at real scale, and you can make it of the size of a cinema screen. So it becomes very intuitive, very immersive. In the field trip that I showed earlier with the geologists in Shell, they did an actual field trip to the sun, and then they did it afterwards in virtual reality. And it was great to hear the engineers saying, the reservoir engineers, the well engineers, saying, I finally understood what the geologist meant, because he could see the thin section, the microscopic thin section, and the log next to the outcrop and to the layer of the outcrop, and where the geologist was pointing and drawing. And so it makes people get concepts faster.
And presumably nothing stops, of course, people looking at this after the day in the field, right? They can
absolutely
in the hotel.
Now they have these headsets such as the Quest, so you can take to the you don't need to connect it to a computer, and you can bring it to the field and have your end of the day session next to it with it. Yeah.
Yeah, indeed. I wouldn't say one would completely replace the other, but they're very complementary. So you can have a field trip where you say, like, there's another few examples that don't happen to be in this continent, but are useful to have a look at now, and you can connect with that.
But at the same time, when, let's say, we were working at the time, I was working offshore Angola, we were exploring for deep water deposits. And we took teams to a field trip in California to see the outcrop models. But, that was a group of us that were the lucky ones, the 20 that we managed to go there. But we had, 120 geologists working on these reservoirs that never got to see the rocks. Yeah. And hence, multiplying that, bringing the data in front of people so that they are able to build better reservoir models and reduce uncertainty and therefore reduce costs, reduce number of dry wells, etc., etc.
And so there is the possibility that you could even be in the field if you got the connection with the headsets on, painting on. It's sort of almost a mixed reality sort of experience. The first questions that are coming in are actually about the type of objects you put in there, and are they in a particular format, and is there kind of standardization required?
Yes, these objects are 3D models that are derived from drone data using photogrammetric techniques. Now, with any drone or even with a handheld camera, as long as you take many pictures of an outcrop, you use a photogrammetric software to create a 3D model. And these 3D models are, the formats are very standard nowadays. It's like OBJs or FBX files. So yeah, and you find free software or paid software to run these models.
Okay. Any more questions? Keep them coming in, please. And are there particular requirements in terms of the specification of the machines you're running on this, or is it fairly standard kit?
So if it depends on the size of the model. So if you're gonna run a model that it's a very large model, and in terms of the mesh, is the grid that is behind the model is quite and the model hasn't been sort of optimized, you might require a gaming machine. But if it's a model that has been optimized and at the right scale, then you can put it on a headset, on a standalone headset, and you don't need a big machine. For that's for VR. For the desktop version, just any modern machine with an i7 processor can run it, no problem. Right.
Do you want to speak as well, maybe about CCS in a wider sense as well, about where you feel are the drivers of success in a CCS project, and how important this technology is?
No, indeed. So there's this example of that. I believe you mentioned the Snowfeed example, where they drilled a well and they found out that good reservoir, they injected in that, and they were surprised how quickly the pressure increased. And they happened to drill into a channel that moved out of plane and was embedded in not so good reservoir. So on seismic, that was difficult to see. But if you would have a good outcrop example, you may have understood that earlier and may have signed your well differently. So I think it's important to look at the fabric on the rock and what might happen to CO2. And I think this tool is a big help with that. Different CCS projects have different problems, and you can find the right analog with that, and then or look at the right core to understand that better. The other thing that Claudia was mentioning is that geologists may understand it, but to explain it to reservoir engineers or production engineers may be more difficult if you just sketch it. So in a virtual field bucket, you can explain what you mean. And I think with CCS project, the integratedness is even more important. In CCS, the geologist is actually downstream of the whole process. Usually we use the hydrocarbons to be upstream, and everybody else catches our product. But here we have to catch the product of the people at the surface. So you have to make sure that you have a really good integrated plan, how you can what operating principles you have, what can be done, cannot be done, and that you understand the risks and uncertainties beforehand. And I think these tools can help with that.
And in terms of the importance, we have heard, from the recent industry acts for net zero, and also from the recent legislation here in the UK, that carbon sequestration is one of the key strategic components in helping us to get to that goal. The UK announced, a very large investment over the coming years, several $1 billion on these type of projects. Ideally, it would be ideal if the technology would allow us to capture the CO2 directly from the atmosphere, but that's not feasible just yet. So while we'll get to that point, people have identified it as a way. A great way to help us get there.
Even when direct air capture is developed, you still need to keep the CO2 somewhere. And if you want to keep it stored for a long term, it needs to be a geological store. So the geological storage, I think, has a much longer future than just CCS.
Got a question here from Peter Gapp from the Maltese Chamber of Geologists. A great presentation. His question is, what role will AI have in the interpretation and interpolation of 3D data from basin to microscopic scale? That's a big general.
It's coming. So actually, and this is something we're working on. At the moment, the interpretations of the outcrop models mostly is being done manually. As we have seen advances of AI on automatic interpretation for seismic, and definitely that's coming to the outcrops and also to the wells. We have seen published many beautiful examples of machine learning algorithms applied to core images. But as always, the models depends how you train the data, and there is not, there is still, you get 60% match, so you still need to correct it by hand, still need the geologists to check the model, but that definitely is coming.
This question is perhaps more of a sort of IT question regarding file sizes. Are you able to send out crops by email, or is this server hosted?
Well, what you saw on here, this is hosted on the cloud. So Jurriaan was calling the model directly from the cloud. But the models, there are models that are of the size of 100 megabytes or 50 megabytes to 1 gigabyte of data. So it will depend on the size of the model. But you usually share it through a server or SharePoint, or in this case, we plug it directly from the cloud.
Right. Okay. Any more questions coming through? We've got a few more minutes. If you have any burning questions out there, we'd love to hear them. While we just wait for that, is there any other things you would like to talk about, Claudia and Jurriaan, about the future of this, about where you see it in 5-10 years' time? Is this how much time are people spending in this environment? What does it look like, do you think?
Well, do I see people living in the digital world and in virtual reality? Probably not. We humans love human interactions and face-to-face interaction and fresh air. So hopefully we will keep the fresh air. But I do see we're going to be using this technology. These technologies are being used not only with digital outcrops, they're being used, for example, with digital twins in facilities, helping people plan visits, etc. So definitely the technology will be there. What is evolving is the hardware as well. So right now the headsets are a bit big, as they're evolving in size, but where this is gonna, and you need the headsets to visualize the big models and to be completely surrounded by the data. But I can see in the near future, you're going to have some fantastic just glasses that will enable us to visualize super highly detailed, big, huge models, and at the same time seeing the real life. Well, it's like AR, but AR at the moment, you know, the models is still, the size of the model and the interaction is still limited with some of the examples we have seen. But we're going to be there, and not only that, we're going to be having live information coming through that too. So it's very exciting, definitely.
Start of the journey. Amazing. All right. We've had no more questions, but we've used up our time very usefully. That hour has gone by so quickly. So thank you, Claudia and Jurriaan, so much for presenting in this webinar. Thank you for the participants who've joined us today. Great to have you with us. In the meantime, take care, and we will see you in our next webinar. Another exciting subject: resources of the moon. By Dr. Oh yeah, make sure you're there for that. Renaud Merle on the 30th of May. Our registrations will open next month in April. So make sure you're there for that. Okay, Claudia and Jurriaan, thanks once again.
Thank you very much. Thank you, Glen.
Ciao. See you soon.
Bye-bye. Ciao.
Bye.